Good morning, my name is Amanda Pettit and I'm going to be delivering training today on atoms, bonds and structure. We're going to go through the learning objectives and then we're going to go through and run through the presentation bit by bit. Then I'd ask for any questions to be left for the end, and then any questions obviously that you've got I'll run through with the answers. Let's get going. So the learning objectives for today will be the various ways metals bond, non-metals bond to metals and non-metals bond to other non-metals. We will discuss electronegativity and how this affects the type of bonding that occurs, explain how the physical properties of substances depend on the type of bonding and structure, discussing electron pair repulsion theory and how this affects the shape of molecules, and give examples of at least 4 of the most common molecule shapes. Explain the different types of forces between ions or molecules and how this affects melting and boiling point and how the sample should be stored. Types of bonding. So there are different types or different ways that items bond together depending on the nature of the item involved. For example, metals bond to metals in different ways to a non-metal bonding to a metal. The different types of bonding that we are going to be looking at are as follows: ionic, covalent, dative covalent and metallic bonding. Electronegativity also affects the type of bonding that occurs, and we will look at this including examples of each. Ionic bonding is the first type of bonding we're going to look at. Ionic bonds are formed between a metal and non-metal, for example sodium chloride. An atom of sodium will lose an electron and form a positive ion. An atom of chlorine will gain an electron and form a negative ion. The ionic bond is electrostatic force of attraction between a positively charged metal ion and a negatively charged non-metal ion. Metals form positive ions because they lose electrons to become stable. An example of this, as the diagram shows there, is magnesium. Magnesium has the electron arrangement 282. To become stable, it must lose its 2 outer electrons to attain a full outer energy level. Atoms are neutral because they have equal numbers of protons and electrons. However, when they lose 2 electrons, they are no longer neutral. They change into ions with a 2 positive charge. Non-metals form negative ions because they gain electrons to become stable. And there's the diagram of how magnesium achieves this. Covalent bonding is the next type of bonding. And then you've got a diagram on the hand side there. Elements having very high ionization energies are incapable of transferring electrons, and elements having very low electron affinity cannot take up electrons. The atoms of such elements tend to share their electrons with the atoms of other elements or with other atoms of the same element in a way that both the atoms obtain octet configuration in their respective valence shells and thus achieve stability. This is known as a covalent bond. Some of the properties of covalent bonds are listed below, including they do not result in the formation of new electrons, the bond only pairs them, which is the diagram that we can see here. Covalent bonds rarely break spontaneously after they're formed. They are directional, where the atoms that are bonded showcase specific orientations relative to one another. Most compounds having covalent bonds exhibit relatively low melting points and boiling points. Melting points and boiling points we'll talk through a lot as we go through the presentation. We've got compounds formed by covalent bonding do not conduct electricity due to the lack of free electrons, and covalent compounds are not soluble in water, to name a few. Covalent bonding continued. Types of covalent bonds. Depending upon the number of shared electron pairs, the covalent bond can be classified into single, double and triple covalent bonds. Single bonds is formed when only one pair of electrons is shared between the 2 participating atoms. It is represented by 1 dash, although this form of covalent bond has a smaller density and is weaker than a double and triple bond, and it is the most stable out of the whole 3. For example, in this diagram here, you've got hydrogen chloride molecule has 1 hydrogen atom with 1 valence electron and 1 chlorine atom with 7 valence electrons. In this case, a single bond is formed between hydrogen and chlorine by sharing 1 electron, and that's the diagram for that one. Double bonds. A double bond is formed when 2 pairs of electrons are shared between the 2 participating atoms. It is represented by 2 dashes. Double covalent bonds are much stronger than single bonds, but they are less stable. For example, as the diagrams show here, a carbon dioxide molecule has 1 carbon atom with 6 valence electrons and 2 oxygen atoms with 4 valence electrons. To complete its octet, carbon shares 2 of its valence electrons with 1 oxygen atom and 2 with another oxygen atom. Each oxygen atom shares its 2 electrons with carbon, and therefore there are 2 double bonds in CO2. Triple bond, which is diagrammed down here, is a triple bond is formed when 3 pairs of electrons are shared between the 2 participating atoms. Triple covalent bonds are represented by 3 dashes and are the least stable type of covalent bonds. For example, in the formation of nitrogen molecule, each nitrogen atom having 5 valence electrons provides 3 electrons to form 3 electron pairs for sharing. Thus, a triple bond is formed between the 2 nitrogen atoms. Polarization of covalent bonds. Polar covalent bond. This type of covalent bond exists where the unequal sharing of electrons occurs due to the difference in the electronegativity of combining atoms. More electronegative atoms will have a stronger pull for electrons. The electronegative difference between the atoms is greater than 0 and less than 2. As a result, the shared pair of electrons will be closer to that atom. Molecules form hydrogen bonding as a result of an unbalanced electrostatic potential. In this case, the hydrogen atom interacts with electronegative fluorine, hydrogen or oxygen. Non-polar covalent bond. This type of covalent bond is formed whenever there is an equal share of electrons between atoms. The electronegativity difference between 2 atoms is 0. It occurs whenever the combining atoms have similar electron affinity. A non-polar covalent bond is found in gas molecules like hydrogen gas, nitrogen gas, and other gaseous elements. It is observed that the sigma bonds between 2 different atoms, the electron cloud is always closer to the more electronegative of the 2 atoms participating in the sigma bond. Due to this, there is a permanent dipole that arises in the bond, and the covalent bond is said to be polarized. Difference between ionic and covalent bonds. You have 2 diagrams there. One is a table of the difference of covalent bonds. Just to very quickly go through the table, which is also in your handout. A covalent bond is formed between 2 similar electronegative nonmetals in covalent bonds, and then ionic bonds, this type of bond is formed between a metal and non-metal. You've got, as you go down, you've also got a diagram of a covalent bond and ionic bond showing the differences. Properties and bonding in compounds. You have ionic lattices, covalent network and covalent molecular. All ionic compounds have a high melting point and boiling point because many strong ionic bonds need to be broken. They conduct when molten or in solution as the ions are free to move. They can be broken down by electrolysis. They are generally soluble in water for the ionic lattice. The covalent network. All covalent network structures have very high melting points and boiling points because many strong covalent bonds need to be broken. They are all hard and do not conduct electricity because there are no free charges that can move. They do not dissolve. Covalent molecular. They have low melting points and boiling points because the attractions between molecules are easy to overcome. They do not conduct electricity because there are no free charges to move. Some covalent molecular compounds have higher melting points than expected, and most do not dissolve in water but may dissolve in other solvents. And then again, you have a table here showing the difference between ionic lattice, covalent network and discrete covalent molecules. Dative covalent bonding, again with a diagram on the hand side. A dative bonder is a sort of covalent binding that is unique. It's a type of alternative covalent bond where the electron pair is shared by only one atom. In other words, the shared pair's electrons are both from the same atom. Because it is a special type of covalent connection, a dative bond is also known as a dative covalent bond. In a covalent bond, sharing is done by both elements, but in a dative bond, only lone pairs of electrons are shared by a single element. The dative bond is also stronger, just like the covalent bond. And then, for example, consider the formation of the ammonium ion, which is the diagram over there. The union of the NH3 molecule with the H+ ion produces the ammonium ion. The core N atom in the NH3 molecule possesses one lone pair of electrons, while the H ion has an empty orbital. As a result, the N atom of the NH3 molecule gives its lone pair to the vacant orbital of the H+ ion, producing a covalent connection. The nitrogen atom in ammonia gives its electron pair to the free orbital of the H+ ion, forming a coordinate bond, which is demonstrated in the diagram here. Metallic bonding and structure. Metallic bonding is a type of chemical bonding when metal nuclei share free valence electrons. These free electrons are called delocalized because they are not confined to one atom. In contrast, valence electrons are shared between two atoms in a covalent bond and spend more time near one atom than the other in an ionic bond. In metallic bonding, valence electrons are delocalized or free to flow between several atoms. Ionic and covalent bonds involve only two atoms. Metallic bonding accounts for many of the key properties of metals. Metallic bonds form between two atoms with similar electronegativity values. Atoms that form metallic bonds are metals and some metalloids. For example, metallic bonds occur in silver, gold, brass and bronze. It is also the type of bonding in pressurized hydrogen in the carbon allotrope graphene. What makes metallic bonding work is that the valence electron orbitals associated with the positively charged nuclei overlap one another. In most cases, this involves S and P orbitals. Metal atoms are bound to one another by attraction between the positive nuclei and the delocalized electrons. Metallic bonding accounts for many of the properties associated with metals as follows: high electrical and thermal conductivity. Free electrons are charge carries in electric conductivity, and thermal energy, heat, carries in thermal conductivity. High melting points and boiling points. Again, strong attractive forces between delocalized electrons and atomic nuclei give metals high melting and boiling points. Malleability and ductility. Metallic bonding accounts for metal mechanical properties, including malleability and ductility. Because electrons slide past each other, it's possible to hammer metals into sheets and draw them into wires. Metallic luster. Delocalized electrons reflect most light, giving metals a shiny appearance. Silver colour. Most metals appear silver because the light is reflected off the oscillating resonance electrons. Absorbed light tends to be in the ultraviolet part of the spectrum, which is outside the visible range. In copper and gold, the absorbed light is within the visible range, giving the metals a reddish or yellowish colour. Electronegativity and polarity. Whether a bond is non-polar or polar, covalent is determined by a property of the bonding atoms called electronegativity. Electronegativity is a measure of the tendency of an atom to attract electrons for electron density towards itself. It determines how the shared electrons are distributed between the two atoms in a bond. The more strongly an atom attracts the electrons in the bond, the larger its electronegativity. Electrons in a polar covalent bond are shifted towards the more electronegative atom. Thus, the more electronegative atom is the one with the particle negative charge. The greater the difference in electronegativity, the more polarized the electron distribution and the larger the partial charges of the atom. Linus Pauling notably described in general electronegativity increases from left to right across the period in the periodic table and decreases down a group. So non-metals, which lie in the upper right, tend to have the highest electronegativities, with fluorine the most electronegative element of all, with it being at 4.0. Metals tend to be less electronegative elements, and the group 1 metals have the lowest electronegativities overall. Covalent bonds form when electrons are shared equally between atoms and are attracted by the nuclei of both atoms. In pure covalent bonds, the electrons are shared equally. In polar covalent bonds, the electrons are shared unequally as one atom exerts a stronger force of attraction on the electrons than the other. The ability of an atom to attract a pair of electrons in a chemical bond is called its electronegativity. The difference in it between two atoms determines how polar a bond will be. In a diatomic molecule with two identical atoms, there is no difference in electronegativity, so the bond is nonpolar or pure covalent. When the electronegativity difference is very large, as is the case between metals and non-metals, the bonding is characterized as ionic. Structures and properties. Again, we're going to talk about melting and boiling points as a start, but the physical properties of substances can be understood through the types of bonding and the molecular ionic structures that compose them. The nature of the bonds between atoms or ions, as well as their arrangement within the substance, significantly influencing its various physical properties, are as following and include its melting and boiling points, its electrical conductivity, its solubility in water, whether or not it's hard or soft as a substance, its physical state at room temperature, which in turn can affect its ability to be used, such as graphite being used to make pencils, making electrodes, and diamonds being used to make artificial joints, components, and blood vessel stents. We will now look at the various different types of bonding and how a substance property affects the type of bonding that takes place. And you also have a diagram on the hand side here explaining between giant ionic, giant metallic, simple covalent and giant covalent, including what I've just spoken about. So melting and boiling points, electrical conductivity, solubility, hardness or softness, physical state of room temperature or at room temperature, forces, particles and examples. Structures and properties continued. Here we talk about ionic bonding and giant ionic lattice structures. So different type of structures and bonding have different effects on the physical properties of substances, such as their melting and boiling points, electrical conductivity and solubility. Ionic compounds are strong. The strong electrostatic forces in ionic compounds keep the ions strongly together. They are brittle, meaning ionic crystals can split apart easily. Ionic compounds have high melting and boiling points. The strong electrostatic forces between ions in the lattice act in all directions and keep them strongly together. Melting and boiling points increase with charge density of the ions due to the greater electrostatic attraction of charges. Ionic compounds are soluble in water as they can form ion-dipole bonds. Ionic compounds only conduct electricity when molten or in solution. When molten or in solution, the ions can freely move around and conduct electricity. In the solid state, they're in a fixed position and unable to move around. In contrast to metallic bonding and giant metallic structures are malleable. When a force is applied, the metal layers can slide. The attractive forces between the metal ions and electrons act in all directions, so when the layers slide, the metallic bonds are reformed. The lattice is not broken and has changed shape. Metallic lattices are strong and hard due to the strong attractive forces between the metal ions and delocalized electrons. Metals have high melting and boiling points. Pure metals are insoluble in water. Metals can conduct electricity when the solid or liquid state. As both in the solid and liquid state, there are mobile electrons which can freely move around and conduct electricity. Again, simple covalent lattices have low melting and boiling points. Compounds are weak intermolecular forces between the molecules. Only a small amount of energy are required to break the lattice. Most compounds are insoluble in water unless they are polar and can form hydrogen bonds, such as sucrose. They do not conduct electricity in the solid or liquid state as there are no charged particles. With giant covalent lattices, they have very high melting and boiling points. These compounds have a large number of covalent bonds linking the whole structure. A lot of energy is required to break the lattice. The compounds can be hard or soft. Graphite is soft as the forces between the carbon layers are weak. Diamond and silicone oxide are hard as it is difficult to break their 3D network of strong covalent bonds. Most compounds are insoluble with water. In this instance, most compounds do not conduct electricity, however some do. Graphite, as an example, has delocalized electrons between the carbon layers, which can move along the layers when a voltage is applied. Diamond and silicon oxide do not conduct electricity, as all 4 outer electrons on every carbon atom are involved in a covalent bond, so there are no freely moving electrons available. Examples and uses of different substances. Medical settings. Diamonds are used to make blood vessel stents, coatings for devices that encourage and facilitate bone growth and or repair. And also gold can be used for fillings for crowns and bridges within the mouth, so for dentistry, and gold therapy can be an effective way to control arthritis. Molecular shape and electron pair repulsion. Electron pair with your diagram on the hand side here. The central atom is the atom that every other atom is bonded to. The central atom forms covalent bonds with all the other atoms involved within the molecule. The shape of the molecule is determined by electron pairs around the central atom. The number of electron pairs found in the outermost shell of the central atom determines the shape of the molecule or ion. The electron pairs can either be lone pairs or bonding pairs. The electron pairs found around the central atom can be either lone pairs or bonding pairs. A lone pair is a pair of electrons that are not shared within another atom in a bond. A bonding pair of electrons is a pair of electrons that are shared between the 2 atoms in the bond, which is demonstrated by the diagram here. You have electron charge clouds following on from the pair repulsion. Electron charge cloud is a region where there is a high charge of electron pair being present. Electron charge cloud is a region of a negative charge around the nucleus, and it is linked to the atomic orbital. Electron charge cloud can contain either bonding pairs or lone pairs of electrons. Any electron pair in the outermost shell of an atom can exist as an electron charge cloud. It does not matter whether the electron pair is involved in a bond or not. Electron charge clouds are as far apart as possible to minimize repulsion. Electron charge clouds are regions of negative charge where electron pairs are found. Remember that like charges repel, so electron charge clouds will repel each other. Lone pair electron charge clouds repel more than bonding pair electron charge clouds. Lone pairs of electrons are held a lot closer to the central atom than bonding pairs of electrons are. Their electron charge clouds are more concentrated and wider. This means that the repelling effect of lone pairs is a lot stronger than that of bonding pairs. The bond angle between 2 lone pairs of electrons is the greatest. The greater the repulsion force between 2 pairs of electrons, the more far apart the 2 pairs of electrons will be, hence the larger the bond angle between them. As lone pairs of electrons have the strongest repelling effect, there is the greatest bond angle between them. And obviously you have diagrams on the hand side showing methane, ammonia and water, and also diagram of the lone pairs have the greatest repulsion to the lowest repulsion of bonded pairs. And then you have the VSEPR model, which is the valence shell electron pair repulsion model, which can be used to predict the shapes of many molecules and polyatomic ions, given the different shapes here. The model can predict the structure of nearly any molecule or polyatomic ion in which a central atom is non-metal, as well as the structures of many molecules and polyatomic ions with a central metal atom. The premise of the polyatomic ions with a central metal atom. The premise of the polyatomic ions with a central metal. The premise of the Vesper theory is that the electron pairs located in bonds and lone pairs repel each other and will therefore adopt the geometry that places electron pairs as far apart from each other as is possible. We can use the Vesper model to predict the geometry of most polyatomic molecules and ions by focusing only on the number of electron pairs around the central atom, ignoring all other valence electrons present. According to this model, valence electrons in the Lewis structure form groups, which may consist of a single bond, a double bond, a triple bond, a lone pair of electrons, or even a single unpaired electron, which in the Vesper model is counted as a lone pair. Because electrons repel each other electrostatically, the most stable arrangement of electron groups is the one that minimises repulsions. Groups are positioned around the central atom in a way that produces the molecular structure within the lowest energy. And here you can see you have the 2, 3, 4, 5 and 6 electron pairs, which equal linear, triagonal, planar, trapheidal, pyramidal, non-linear and triangular, pyramidal, seesaw, T-shaped, octahedral and square planar. And then finally, how to store samples. The state of a substance, solid, liquid or gas at room temperature is primarily determined by the following factors: intermolecular forces, temperature, pressure, molecular structure, phase diagrams, to name a few. So basically, intermolecular forces, different types of intermolecular forces influence the arrangement and the energy of particles. Stronger forces like ionic or hydrogen bonds tend to hold particles closer together, resulting in solids. Weaker forces like van der Waals forces allow for more movement between particles, leading to liquids and gases. Temperature affects the kinetic energy of molecules. As temperature increases, molecules move faster, which can overcome intermolecular forces. For example, heating a solid may cause it to melt into a liquid, hence putting it into another state. Pressure. Changes in pressure can alter the state of a substance. For instance, increasing pressure can force gas molecules closer together, potentially turning them into a liquid or solid. Phase diagrams. Phase diagrams illustrate the conditions under which a substance exists in different states. The position on the diagram indicates whether the substance will be a solid, liquid or a gas at any given temperature and pressure. Example, water at room temperature. Water is a liquid due to its hydrogen bonding, which is strong enough to keep molecules close but not so strong to hold them in a fixed position like in a solid. And carbon dioxide at room temperature and atmospheric pressure. Carbon dioxide exists as a gas because its intermolecular forces are relatively weak. The state of a substance at room temperature is a result of the interplay between intermolecular forces, temperature, pressure and molecular structure. And then lastly, in order to demonstrate that different substances need to be stored in different ways, we're going to consider the following substances and explain how these need to be stored, and in some instances explain some storage precautions. Magnesium. Store in a sealed container, store in a cool, dry area, protect from moisture and do not store together with oxidizers, acids or halogens. Silicon. In the example of silicon sealant, we need to store in a cool and dry location where the temperature is between 5 and 25 degrees. Argon. In the example of argon gas, cylinders should be stored upright in a well ventilated, dry, cool, secure area that is protected from the weather and preferably fire resistant. No part of the cylinder should ever be allowed to exceed 52 degrees. Never deliberately overheat a cylinder to increase the pressure or discharge rate. Cylinders should be stored away from heavily travelled areas and emergency exits. Avoid areas where salt and other corrosive materials are present. Boron. Store in tightly sealed containers, store in a cool, dry area, protect from moisture and do not store together with acids, strong oxidizers and halogens. And lastly, fluorine. Teflon is the preferred gasket material when working with fluorine gas. Keep equipment scrupulously dry. The reaction between metals and fluorine is relatively slow at room temperature but becomes vigorous and self-sustaining as the temperature is elevated. Store and use only in ventilated gas storage cabinets or fume hoods. Process valves should be opened and closed with remote controlled extensions passing through a suitable barricade for additional protection. Double valving should be employed to facilitate the reduction in pressure from high pressure sources of fluorine. Fluorine reacts with many materials normally recommended for handling compressed gases. Thoroughly review the incompatibilities before working with this substance. Use and store fluorine in a ventilated gas cabinet or fume hood. When a gas cabinet is warranted, e.g. cylinders larger than lecture bottle size for that are used in a fume hood, install a fluorine gas monitoring system. Follow all applicable recommendations for storage and handling compressed gases. And finally, they are the references for all of the information that I used within this presentation. And now I'll take questions. Thank you.